Here at the Moist Tube Department. My name is Matthew Cole, and I'm here with Nathan Draper, Anthony Forrest, Daniel Canesso, and John Polly. Our test experiment studies icing on pitot tubes. Our test objective is to reliably form ice on pitot tubes with the goal of observing pressure differentials resulting from the ice blockage. Our key question is, how can ice formation on a pitot tube be inhibited? The background of this experiment is as follows. During flight, a plane's velocity is measured using pitot tubes. These tubes can freeze, clogging pressure holes and causing errors in pressure and velocity measurements, which can be catastrophic. The significance of this study could be immense, as finding a way to prevent icing pitot tubes would increase the safety of flying by decreasing the possibility of incorrect pressure readings. The results of the simulation are shown here. Freezing occurs faster with higher airspeeds, as well as with lower temperatures, which is to be expected. Formation of ice in the test provides a proof of concept for a larger scale operation with lower temperatures and higher airspeeds.
My name is Daniel Canesso. I'm going to be going over the first portion of methodology, including the test plan, experimental conditions, variables, and parameters in the experimental setup. So for our test plan, we needed to create a climate-controlled environment, and we did this through use of a chest freezer. This environment allowed for the system to simulate temperatures at high altitude conditions. The temperature in the freezer ranged between 0 and 10 degrees Fahrenheit. These temperatures were cool enough to allow for ice to be accumulated on the pitot tube. For our recirculating wind tunnel setup, a powered fan circulated air through a flexible aluminum duct system located inside of the freezer. This fan allowed for the test to maintain steady airflow inside of the duct and onto the pitot tube. The pitot tube was inserted through the lid of the freezer and positioned in line with the flow. A grommet was placed on the top of the chest freezer to create a secure seal in the environment. The pitot tube was then inserted through a hole in the top of the duct and oriented so that it faced the airflow. For our water nozzle, a spoon head was attached to the end of a brass fitting with a small hole drilled into the top. This laminar stream exerted by the drilled hole hits the spoon and dispersed the water across the surface of the pitot tube. The spoon atomizer was installed a few inches upstream of the pitot tube, just far enough so that ice formation was possible. The brass fitting was connected to a water tube that was powered by the Arduino. For our electronics, we had an Arduino microcontroller controlling the water spray onto the pitot tube. The Arduino automatically moved the water to the spoon atomizer through 5-minute time intervals. The blower fan was connected to an external power supply and ran at 12 volts. So originally we tried to use a pressure transducer to improve the results of the testing and mitigate human error, though this came with problems as the velocity of the blower fan on the pitot tube did not flow fast enough and therefore the transducer was displaying negligible results. After speaking with Professor Hoover, we decided on using a vertical manometer, and this provided us with more prominent data. These results were recorded by eye and allowed us to track the pressure differentials in real time. For experimental conditions, variables, and parameters, starting with the independent, the key variable we changed was the presence of water spray. This determines whether ice would form and affect the pressure differential. For the dependent, what we measured was the pressure differential across the pitot tube. Changes in this value indicate that ice is affecting either the static or dynamic ports. For our controlled, to isolate the impact of water spray, we kept other conditions constant across all tests: the fan speed, internal freezer temperature, spray timing, and pitot tube orientation. And our fixed parameters. Some things never changed at all between the tests. The total test duration being 30 minutes, the water reservoir temperature being 70 degrees, the misting method using the spoon nozzle, and the airflow direction. These fixed parameters created a consistency throughout all of the trials. So starting with our experimental setup, depicted on the left is the duct system and on the right are the preliminary electronics. Right here we can see the water tube that is connected to the Arduino reservoir. It's coming right here, it's hitting the spoon, which is then dispersing the water onto the pitot tube, which is getting inserted through this hole. It's going to be facing this way because the direction of the airflow from the blower fan is coming in this way, recirculating this way around. This is connected to an external 12-volt power supply. The Arduino, on the other hand, is connected to a breadboard, which is connected to a reservoir here pumping the water into the system. So for the experimental setup for the test chamber, on the left is a schematic of what's going on the right. As you can see, the pitot tube is extending up through the lid of the chest freezer and it's connected to a manometer. Can't see what's going on inside of the freezer, but right here, this is coming down and coming into this inlet, and then this system is going to run. Depicted here is a side view of the test chamber. As you can see, the pitot tube is going in. Right here, we can see the reservoir of water, which is leading the hose up and through the bottom of the freezer and onto the spoon. The wires are coming out from the blower fan, which are connected to an external power supply. So for the experimental setup for the electronics, the Arduino is connected to a relay, which is connected to the water outlet as well as the power supply. The positive side of the power supply is connected to the water inlet, which is the reservoir. The fan is operated on a simple switch system connected to a power supply. We can turn it on and off as necessary.
To take the measurements for the slab, we used a pitot tube connected to a manometer. The pitot tube allows us to get the two pressures that we need, which is the static pressure gate, which we get from the side of the pitot tube, and the total pressure, which we get from the front. The manometer allows us to read these results and be able to analyze the data later. The equipment we used in our lab was primarily found in the MAE lab that we were able to acquire for free. The equipment we used was the pitot tube, a chest freezer, the electronics instructional materials. The two things that we had to acquire elsewise was the ductwork for the closed loop system, as well as the atomizer. For our schedule, we use a Gantt chart. For our Gantt chart, we were able to snapshot a photo of week 7 to current, clearly showing where we started our projects and when we expected them to end. For the most part, we were able to follow it pretty closely. We found that what took the longest is the gathering the information originally, as well as doing our findings for the data. For the budget, since most of our items were able to be acquired from the lab, we didn't have to pay anything for those. While the two things that we didn't acquire from the lab that we actually acquired from Lowe's cost us roughly $22, with the ductwork being roughly $15, and the nozzle and atomizer were roughly $7. So this is a very low cost, low risk experiment. For our risk assessment, we didn't have too many things that could cause injury or harm to people. The two things that were the big parts of our lab that could be seen as dangerous were the low temperatures, which could freeze or burn your hand, as well as the electrical components from the pump not being sealed off properly. So those two can be very easily mitigated by taking very careful care of the cold items, as well as making sure the wires are connected properly.
Okay, so now we are moving on to the results section. You can see this is our first data table for all of the raw data that we collected off of the manometer. The first control test here, we had no water running into the experimental setup. So as expected, all of the pressure readings were the same. The trial 1, 2, and 3 all had water running into the duct system, and we saw a change in pressure readings on all of those trials. So here's the data from that last data table visualized in a graph. You can see we have time on the x-axis and the different pressure values on the y-axis. The control test is shown by this solid line. You can see that it stays constant the whole time. Trial 1, 2, and 3 seem to start deviating around the 10-minute mark. That's when the pitot tube starts to ice over and that static and dynamic hole start clogging, and it's throwing off the pressure reading. So as you may have noticed in the last slide, not all trials started at the same initial value. So to better visualize the data, we subtracted each preceding value from the value that was first taken on the pressure reading. This just showed the difference in pressure throughout our trial. Here's the resulting graph from that data table. You can clearly see the spread of changes in pressure value over time from trial 1, 2, and 3. So as you can tell, looking at those two graphs, the the ice had significantly impacted our pressure readings post 10 minutes on our trials. To confirm the validity of our test and see that there was no errors, the control test was observed to have no change in pressure. So you may have noticed on the graph that there wasn't either a constant upward shift or a downward shift in the data. This is because an upward shift happens because of a blockage in the static port, and a downward shift happens because of a blockage in the dynamic port. The ice didn't form uniformly over the pitot tube during the trial, so as different ports were blocked, the data changed accordingly. Because this was a lower budget proof of concept experiment, there are a couple sources of error in our procedure. To start with, the system had to be repositioned after a test because ice kept forming in our duct and it would clog up our fan. And when it was cleared of that ice, the fan orientation may not have been perfectly set in the same place that it was during the previous trial. The manual manometer readings are subject to human error because we were just looking at the values with our eyes, and we could have been a tenth of a millimeter off in either direction. Temperature variations changed because we were opening and shutting the cooler in between trials, and the atomizer didn't uniformly or perfectly atomize the water in every single trial.
My name is John Polly. We're going to move on to the conclusion. Referring back to the test description, we do prove the concept of ice formation on pitot tubes. Our pressure readings fluctuate randomly on each test, which is a problem planes would face outside of the lab. The experiment we designed with the equipment on hand was successful and low budget, though it would have cost a couple $1,000s to run from the ground up. It was low budget in our case because most of the equipment was in the lab, and we did have ice formation on all of our trials that resulted in a pressure discrepancy. There were a lot of possible errors with our experiment. To start, we had a closed, opaque cooler that made it impossible to actually see what was going on inside of the cooler, and we had to go off the feel. We used the manometer to get the most direct flow into our pitot tube, and during each experiment, the water would clog up the fan and nozzle. It'd form ice that had to be cleared out between every trial, and it completely changed our starting conditions every time, and could have changed things like duct friction and airspeed in the environment. Obviously, there could have been human error while reading the manometer and getting the pitot tube to have the best orientation for pressure readings. Cooler also had to be slightly open to let the nozzle tube in the environment. Originally, we had it pulled through the drainage port, but the water would freeze inside the tube and we couldn't get a full trial with that setup. For future work, we can work on different de-icing methods. We could test the efficacy and efficiency of industry standard heated pitot tubes, as well as different paints or chemical coatings that we could apply. We would also use a more industry standard test setup and include a wind tunnel similar to those in the lab that have climate control functionality. We could also use a nozzle similar to the one in the diagram that would atomize the water further, which would give us a better and more even covering of ice. And the results from that test could be used for reproducibility tests because they'd be more accurate than our current results. The Moist Tube Department would like to thank Professor Hoover and his TAs for their full support throughout this project. Access to the MAE lab at Clarkson and the supplies in the machine shop were vital for the success of our project. The Moist Tube Department used AI responsibly through the development of our experiment. ChatGPT was used for multiple parts, including searching for common avionics issues, and the idea of pitot-static tube ice formation was found doing this. We then prompted the AI to make a test setup with a budget, which was the grounds for how we started our experiment. We also used it for data analysis, verification, and help with coding the microcontroller relays.